Thanks for the introduction. Yeah, I would like to talk about the concept of best matches and best match graphs. And in the second half of my talk about a bit of a more specific problem, that is the complexity of best match graph editing. So first, of course, I want to give you a definition of best matches, at least as we define them. And for this, you need a rooted tree. And this tree represents the history of a gene family. And then you, of course, have leaves, and those leaves represent the extant genes, so the ones that we are able to observe right now. And usually for an extant gene, it's of course known in which species or genome it resides, and this is encoded with the coloring. So the same colors mean that those genes are in the same species. And for this tree here, this for example, have been produced by a scenario like this. So you have a species tree in the background, and then within the species tree, the gene family evolves. But for gene trees, you don't only have speciation events, which are the circles, but also things like duplications, for example, which are the squares. So you have additional branching events. So this is actually the same tree like this one here. So what are best matches? A best match, let's say of gene A1 with respect to some other color, let's say the blue color, are those genes of the blue color that have the lowest last common ancestor, or LCA, with that gene. So if we look at A1 and the blue genes, then the best match in this case would be only B1, because the lowest LCA to any of the blue genes is this one here. In contrast, B2 has this one here as last common ancestor with A1. So this here is strictly above this one, and therefore B2 is not a best match of A1. But if you now look from the perspective of B2, then A1 would be a best match, since there's no other red gene that has a lower last common ancestor than A1. And in contrast, those two wouldn't be best matches since they have this one here on top. So best matches are not symmetric. And maybe one last example, the best matches of C2 with respect to the red color are both A2 and A3, since they both have this one here as last common ancestor. So best matches to some color are also not unique. Yeah, and this relation can be expressed in a directed colored graph. And for this example here, this produces this graph, and you have to read it like this. If you have an arc from, say, A2 to B1, then this means that B1 is a best match of A2. So we always have arcs pointing towards the best matches. So A2 pointing towards B1 and also to B2 in this case, because they both have this one. And this graph is called the best match graph of this tree, or in short, BMG. And since this tree produces this graph, we say that it explains it. Yes. So I've basically given you the definition of best match graphs of some specific tree. But if we now look at some arbitrary colored digraph, then this graph is a BMG whenever it can be explained by a tree. So whenever I were going to ask in the following, is a graph a BMG, then I actually ask, is there a tree that explains this graph? Yes. I also want to give you some motivation why we are interested in looking at best matches. And the main reason for this is that reciprocal best matches, that means a pair of genes for which arcs in both directions exist, like for example, all of these three here, they are a very close or a very good estimate for orthologs. And orthologs means the two genes, let's say for example A1 and B1, have a speciation event at their last common ancestor and not a duplication or horizontal gene transfer or whatever. And orthology is interesting since orthologs are in general assumed to have essentially the same or at least very similar functions across different species. And even though this conjecture is a bit controversial, it's still used for functional gene annotation a lot. And also orthology is essential in phylogenomics So if you want to estimate species phylogenies from genes or from gene similarities, then you would probably only want to look at pairs of genes that diverged at the same time as the corresponding species and not something that diverged up here or somewhere else. Yeah, and it turns out that if you don't have horizontal gene transfer, so no genes can be transferred between the branches of the species tree, then the orthology relation or the orthology graph is a subgraph of the reciprocal best matches, so of the when we only retain the bidirectional arcs. And therefore, best matches are usually an intermediate step in the so-called graph-based orthology detection tools. And those are tools that try to estimate orthology directly from sequence similarity without explicitly constructing a gene tree, because this is expensive or error-prone, or we just don't want to do it. So we get a graph that is directly based on the similarity of genes, of the extant genes that we can observe. And of course, this has some problems because the data always contains noise and also systematic errors. And by systematic errors, I mainly mean that the shortest distance, or which is more or less equivalent to closest similarity, is not always the same as closest relatedness in terms of last common ancestors. And to see this, the meanest example that you can build is probably this one here. Here the heights of the vertical part of the lines represent the distance. So those two genes would have the shortest distance, since if we add it up, we get 3. Whereas the actual best matches for both of those genes are this one and this one. So we would think that those two are reciprocal best matches, even though they are not best matches in either direction. So what we are usually getting is an estimate that is not a valid BMG. So there's no single tree that explains it. And this is a bit of a problem if we want to apply our nice mathematical results for the relationship for best match graphs and orthology, since they usually require this property that we have a valid BMG. And this brings us to an editing problem where we are given a colored digraph and we want to insert or delete as few as possible arcs in order to give you a valid BMG that can be explained by a tree. And for this optimization problem, I've given you here the decision version. So we have some arbitrary colored digraph and an integer k, and we want to have a set f of arcs of cardinality at most k, such that the symmetric difference of those arc sets gives us a valid BMG. And this is the problem that I want to talk about in the second half of my talk. But before that, I want to give you some more general results and some intuition for best matches. And I want to start with this one. So this is again the example from before and the definition of best matches or arcs in short. And one important property of best match graphs is that every arc has an out neighbor or best match of every other color. So I think this is quite intuitive. So if we have some vertex and another color, then we are looking at those vertices of the other color that have the lowest common ancestor. So there always be one that has the lowest common ancestor, last common ancestor. And therefore we get an out neighbor of every other color for each vertex. And we call this property of a graph sync-free colored, since if we have only two colors and a properly colored graph, then this actually reduces to sync-free in digraphs. Yeah, and another property of least resolved of best match graphs is that they can be explained by a unique least resolved tree. And least resolved tree here means that we have a tree in which we cannot contract any edges without modifying the graph that it explains. So in this example here that I've drawn is actually not least resolved, since, for example, if you look at these 3 genes here, they all have different colors. So this edge here between those two does not matter. We can simply contract it and we still get the same BMG. And the same is true for this edge here. We can also contract this one and it doesn't change anything. So those two are the only redundant edges in this example, and we get a least resolved tree that looks like this for this graph. Okay, and if we want to characterize or recognize BMGs, then it turns out that rooted triples are very helpful. A rooted triple is a binary tree on 3 leaves. And if we have 3 genes, say A, B, and B prime, then we get exactly 3 possible triples, so these 3. This one, of course, is also a possible topology, but it isn't a rooted triple since we have this polytomy here. Yeah, and what interesting cases that give us some topological information for the trees that explain BMGs are essentially 2 cases, and it's always a combination of 3 vertices where exactly 2 have the same color. And the first interesting case is this one, where A only points to B and not to B prime. And here the dashed arcs mean that those arcs may or may not exist. They are not important. And this thing here implies that the LCA of A and B is strictly below the LCA of A and B prime. And this can almost immediately be seen from the definition of best matches. So this essentially means that every tree that explains a BMG with this thing as subgraph must display this triple. Yeah, and the other case looks like this, that A points to both B and B prime. And this means that the LCA of AB and the LCA of AB prime must be equal. So for the topology in every gene tree, we have either this case or this case. And those 2 are forbidden. And to see this, we could simply assume that we have a tree that displays this triple here. Then, of course, the last common ancestor of A and B would be strictly below the other one. So this triple would immediately contradict that we have an arc from A to B prime. So what we can do is we can simply go through our graph and look at all combinations of 3 vertices where exactly 2 have the same color. And then we get a set of informative triples. So this one implies this one. And a set of forbidden triples. This one implies not this one and not this one. And all of those triples must be displayed by every tree, and all of those triples must not be displayed by every tree that explains the graph. So and it turns out that these 2 triple sets are already sufficient to characterize BMGs. And there are two ways that you can do this. The first one is that you only look at the informative triples, R, and you have to check whether they are compatible. So compatible means, is there a tree that displays all of these triples in R? And of course, I think most of you know that there's a well-known algorithm called build that can check whether a triple set is compatible, and if so, construct a tree that displays all those triples. And I will denote this this tree by Aho, since Aho et al, Aho of R and V. So I will also explicitly give the vertex set. And then if this is compatible, in the second step, we only have to check whether the BMG G of this tree is equal to the original graph. And then we get that your original graph was a BMG. This is also, it's kind of trivial because this is the BMG of a tree, so it must be a BMG by definition. And the second possibility is that we look at both the informative and the forbidden triples and have to check whether this pair is compatible, where here compatible means that is there a tree that displays all of those triples and none of those. And for this task, there's also a polynomial time algorithm called MTT by He et al. And whenever this pair is compatible, then we only have to check if the graph is sync-free colored. So does every vertex have an out neighbor of every other color? And then this thing is also a BMG. So we have two ways to recognize BMGs in polynomial time. And this means that the BMG editing problem is an NP. Because if we are given a solution of the problem, so a graph, then we can verify whether it is a BMG in polynomial time. But before I want to continue with the complexity, maybe a little spoiler, it will turn out to be NP hard. I want to talk about a subclass of BMGs, and that is the BMGs that only have two colors. Because two-colored BMGs, or two BMGs in short, and especially their least resolved trees, have a much simpler structure. And this is an example for such an LRT for 2BMG. And one important property of them is that every inner vertex is adjacent to at least one leaf. And another important property is that every subtree under an inner vertex contains both colors. And what this means is that we can essentially directly look at the least resolved tree and see all the out neighbors of every vertex, because we just say we look at this one, then we just have to look at the inner vertex to which it is attached, and all its out neighbors are exactly the ones of the other color that are within the subtree. So for this one, we would get those two white ones as out neighbors, because they all have this one as lowest last common ancestor. And for example, the white ones on the root, of course, have all of the black ones as out neighbors. So this would be pretty helpful in the proof that I want to show you in a second. Yeah, and the second nice thing about 2BMGs is that they can be characterized in terms of forbidden subgraphs. And it turns out that there are 17 non-redundant forbidden induced subgraphs for 2BMGs, which fall into three classes. And here, with the dashed arcs again, mean that those arcs may or may not exist. But whenever I haven't drawn any of the arcs, then those arcs must not exist. So maybe only to give you some intuition why this one is forbidden. I've just told you that whenever we have an arc from x1 to y1, let's say, for example, this one is x1, then we can say that y1 must be in the subtree of the inner vertex to which x1 is attached. So it is either this one or this one. And if we can apply now this argument along the path from x1 to y2, and can then say that y2 must be also in the subtree, and therefore it must also be a best match of x1. But this arc here is missing, so this is why this subgraph is forbidden. Yeah. Okay, so now in the second half of the talk, I want to talk about the complexity, not of the general problem of best match graph editing, but at first only of 2BMG editing, which is obviously a sub problem, and therefore also in NP, since we can recognize BMGs in general, and therefore also BMGs that only have two colors. And to show you that it is NP hard, I will use a reduction from a problem called exact three cover. And exact three cover is actually one of Karp's famous 21 NP complete problems. And it looks like this. We are given a set S that has a cardinality, which is a multiple of 3, so 3t, where in this case t is 2. And by the way, the coloring doesn't matter, it's just for visualization. So we have the set S and also a set C, which contains 3 element subsets of the set S. So like this one here. And the question is there a subset C prime of C that has a cardinality of T and whose union, so the union of all the sets in the C prime, again give us S. So how does this have to look? We have to find sets that are non-redundant. So none of these elements must appear twice. And the union again must just give S. And it turns out that the example that I've shown you here has a solution, because we can simply pick the first one and the last one, and together they give us the set S and have a cardinality of 2. Yeah, and in order to use this to show that 2BMG editing is NP-hard as well, we would now have to construct or take an arbitrary instance of exact3 cover and construct an instance of 2BMG editing and show that this instance has a solution if and only if the original instance has a solution. And this is exactly what I'm going to do. So I will use a reduction that is very similar to the one that was used to show that cograph editing is NP-hard. And I will proceed as follows. At first, I will take the set S and construct for or create for each of the 3T elements in S a black vertex and a white vertex. So since there are 3T elements in total, we have a black and a white one for each, we get 6T vertices so far. And I will also add all arcs between differently colored vertices. So this is actually a property that I will always maintain. So arcs are only between vertices that have different colors. So in this thing here, we will have 18 T² arcs in total so far. And I will denote this number by R. And also if whenever I have a set that contains, or a subgraph that contains black vertices and white vertices and all the arcs that are possible, so between different colors, then I will call this a biclique. Yeah, so now we've done something for the set S, and now I'm going to construct something for the subsets of S in C, and there are M in total. And for each of those M subsets, I will create something that I call an XY gadget. And those gadgets look like this. I've drawn here a zoom in of one of the parts of one gadget. So it consists of two bicliques. One that is called X, and X has R white vertices and R black vertices. So R was this number here. And since it's a biclique, all possible arcs in between. And there's another biclique called Y, consisting of Q black vertices and Q white vertices, and again, all arcs between them. And Q is this number here, and I think it will be clearer later on why this number has to look like this. And additionally, we will add all the possible arcs from the X part of the gadget to the Y part. So all from the white ones to the black ones, and from the black ones to the white ones, but not in the other direction. This is important. So it turns out that each of these gadgets can be, or is a tree, is a BMG, since it can be explained by a tree that looks like this. So here, all of the elements in X are directly attached to the root. So we have all of the arcs between them. And the same is true for all of the elements in Y. They are directly attached to this one. So we have all arcs between them. And since all the vertices in Y are in the same subtree to which those here are attached, we also get all arcs from the X vertices to the Y vertices. So exactly what we want here. And not the ones in the other direction, because every Y vertex is attached to this one, and we don't get outside of this subtree with the out neighborhood of these vertices. So every of these gadgets is in itself a BMG. So to recap, we have done something for the set S, and also for the subsets of S in the set C, which are the M gadgets. And now we have to model somehow the relationship between the two. So remember, each of these subsets contains exactly 3 elements of S. So what I'm going to do is I'm going to add all possible arcs from some gadget to an S vertex whenever the corresponding S vertex was or is part of the corresponding set C. So this looks like this. Every gadget then has out arcs to exactly 6 vertices, representing 3 elements of S. And in this example here, S1, S2, and S3, so we have arcs to those three, must have been part of the first subset C1. So this is the overall construction that we are going to use, and this now encodes as our original instance of exact3 cover. Yeah, and it's quite huge, but it can be constructed in polynomial time because it has only this many vertices, which is a lot, but still polynomial. So we are fine. And my claim now is that this monster here with a k, an integer k that looks like this, has a solution if and only if the original instance of exact3 cover has one. So we have an if and only if that we have to prove. So two directions. And the first direction is a bit simpler. There we assume that we already know a solution for exact3 cover, and now show that this graph here with this integer also has one. And to show you this, remember how a solution of exact3 cover looks. So we have subset C prime of C that has a cardinality of T that exactly covers the set S. So what I'm going to do, I will, this is already done here, I will cut off all the arcs from the X part of the gadgets to S vertices whenever the corresponding set is not part of the solution. And in contrast, I will only retain arcs from the X vertices to S whenever the corresponding set is part of the solution. And this already implies us that we have 6r times m minus t deletions. So we had 6r times m in total before, and we only retain t times 6r of the arcs, so we have to make this many deletions. And we will also, down here, delete all arcs between S vertices that are not part of the same set on the solution C prime. So what we get here is an induced subgraph that is a disjoint union of bicliques, where every biclique contains exactly 3 white vertices and 3 black ones. And every such biclique therefore has 18 arcs. And since there are t, we only retain 18 t arcs, and we have down here r. So we have to make another r minus 18 t deletions. And this here plus this exactly was the k that we had defined. So to show the first direction, we only have to prove that this actually is a BMG. And to see this, I've already told you that each individual gadget is a BMG, since it can be explained by a tree that looks like this one. And if we now look at the other connected components, which are still attached to S vertices, then we can also explain this by a tree that looks like this, where we only add another inner vertex to which all the vertices in S are attached. So we have all arcs between them, and also all arcs from the X part of the gadget to the S vertices, since they are all part of the subtree. And but we don't get any arcs that point outside of the subtree, since this subtree contains both colors. So each connected component is a BMG, and if this is the case for a graph, and every of the connected components contains all colors, which are in this case only 2, then the whole thing is also BMG, because we can simply go and attach all of the trees to a common root, and then this tree explains the whole thing. So we have a solution for 2 BMG editing, since this thing here is a BMG, and we made only k edits. Okay, so the other direction is a bit trickier. And here we assume that we have a solution of 2 BMG editing. And what I'm going to show you, what I'm going to try to convince you, that we have to make arc modifications here in a very specific manner that again gives us something that is very similar to what we've seen here. And so we have this graph as input and a k that again looks like this. And what will be very helpful is that we've chosen Q such that it is higher than 2k. So Q was the number of black vertices and white vertices in every of the Y parts of the gadgets. And the reason for this is that if we have at most k modifications, then we can affect at most 2k vertices, because every arc has a head and a tail, and if they are all independent, then we affect exactly 2k vertices, so we cannot affect more. And this helps us because this means that in every Y part of the gadgets, we will find a black vertex and a white vertex that are not affected at all in the solution. And so neither in neighborhood nor out neighborhood changes. And this will, for example, be helpful to prove the first claim. So there will be 3 in total. And this is that every S vertex, so one of them here, has in arcs from at most 1 gadget. And to see this, we can assume for contradiction that we have in arcs from different gadgets, and then we we can choose unaffected vertices up here, and we get an induced subgraph that looks like this. So we don't have any arcs here on the diagonal, and this gives us a forbidden subgraph of type F3. So we can conclude that we cannot have in arcs from 2 gadgets. So now we can ask when is the maximum number of arcs that we can retain between X and S vertices. And this is then exactly the case if every S vertex or every S vertex has in arcs from exactly 1 gadget. And in turn, this maximum number of retained arcs between in here gives us a minimum number of deletions that we have to make. And those are again here. Since we had 6R times m before, and we only can retain at most 6R times t, then we have to make at least this many deletions. So, and you can see that this is already the first and the biggest part of our budget. And now we can ask what would happen if some S vertex does not have any n arcs from a gadget. And this would mean that we have to make another 2R deletions, and this is not this is less than the rest of our budget. So we can conclude that every S vertex has in arcs from exactly one of the gadgets. And by the same argument, we can also say that these arcs must have been there in the original graph, since cutting an S vertex off and then reattaching it to something else is not within our budget. The second claim is shown in a similar way, and it says that we do not insert arcs between the X parts of 2 distinct gadgets. And again, we can assume for contradiction that we do such a thing. Then we find vertices that are unaffected here in the Y part of this gadget. And in particular, this vertex and this vertex do not have any arcs in between them. So they are independent, and therefore we get an induced subgraph that is of type F1, where these two are independent. And so we can conclude that this is forbidden and we do not insert any arcs between them. So this is only a technical result that will be useful for the third and last claim, which says that we do not retain any arcs between S vertices that have in arcs from distinct gadgets. And to see this, we will again assume that we do have an arc left between 2 S vertices that have in arcs between distinct gadgets from distinct gadgets. And we have just shown that we have not inserted any arcs between those 2 vertices, and therefore we again get a forbidden subgraph of type F1. And therefore we can conclude that this claim is true. So we had already from the first claim deleted arcs between or in between here, and now the third claim implies that we have to make another a whole lot of arc deletions down here. And again, we can ask, when do we reach the maximum number of arcs that are retained down here? And since every S vertex is still connected to some X gadget, and these arcs must have been there in the original graph, this means that we could at most again get connected components that are cliques, that are bicliques consisting of 3 black vertices and 3 white vertices. So we get exactly what we've seen before. Or why do we get this? Because this maximum number of retained arcs again gives us, of course, a minimum number of deletions that we have to make. And if you remember, the 6 vertex cliques imply that we had made R minus 18t arc deletions, and this is exactly the rest of our budget. So when we can conclude that we actually get bicliques that where each contains 3 black vertices and 3 white vertices. And we also know that they are each connected to their to a gadget. And this means that for every such biclique, we can conclude that the 3 elements were part of the original set. So, and since every S vertex is connected to some of the gadgets, this exactly gives us a solution of exact 3 cover, since we can now go and just take all the gadgets that still have arcs to some S vertices and construct the solution C prime in this way by just taking the corresponding sets. Yeah, so now we have shown that if we had a polynomial algorithm for the solution of 2 BMG editing with this K, where's my mouse pointer? Oh, there it is. Then we could also solve the exact 3 cover problem in polynomial time. So this is not possible, and therefore 2 BMG editing must be hard as well. So I hope I could convince you a bit that this problem is hard. I still haven't talked about the general problem. I think it's quite intuitive that if the problem is hard for 2 colors, that it won't get any easier for more colors. But anyways, we have shown it for an arbitrary number of colors simply by reduction from 2 BMG editing. And the main idea is to take an instance of 2 BMG editing and add in another L-2 colors and 1 vertex of each of those new colors, and then attach them in a way such that no optimal editing will ever touch them. And this then proves that, or establishes that the general problem is also hard. Yeah, we also looked at variants of the problem. And the first one is BMG deletion, which means that we are only allowed to delete arcs. And you may have noticed that in the proof, we only ever deleted arcs. So we can actually take the same proof to prove that this one is NP hard as well. And the second variant is BMG completion. And that means that you are only allowed to insert arcs. And this requires a different proof, but we could also show that it is NP hard by reduction from chain graph completion. Yeah, so they are all hard, but anyways, we still have an exact solution for them, since we have an integer linear program formulation, and ILP graph editing methods usually try to minimize a sum that looks like this. So here the capital E means that, or if this variable for xy gets 1, that means that the arc xy was present in the original graph and 0 otherwise, whereas the epsilon are the binary variables that encode the arcs in our solution. So they get 1 whenever xy is, or they get 1 in the optimization process whenever there's an arc between x, or from x to y. So if we now sum over all sorted pairs, x and y, then the first part of the sum gives us the deletions, and the second part of the sum gives us the insertions. So and what we actually did is we explicitly modeled a tree using ILP, variables and constraints. And this is done by using variables and constraints from this paper here. And we additionally added binary variables for all possible triples, and then used our characterization of BMGs that says that a BMG must be symmetry colored. So every vertex has an out neighbor of every other color. And that none of the informative that all of the informative triples and none of the forbidden triples must be displayed. So you may remember informative and forbidden triples were defined in terms of the presence and absence of arcs and of the coloring of the involved vertices. So we can simply add a constraint that whenever we get an informative triple, then this forces this binary variable to be 1. And whenever we have a forbidden triple, this forces to be 0. So in this way, we get an exact solution for the problem. So it works like for up to 10 vertices in a couple of minutes on my laptop. So it's not super cool, but the problem is hard after all. And this also ensures that I still have work to do, because one thing I'm working on right now is the development of efficient heuristics. And the main idea for this at the moment is to use informative and forbidden triples, which can be defined for or extracted from arbitrary graphs, and then do something that is similar to build, but somehow handle inconsistencies. And we haven't yet tested any of the heuristics on real life data. So this will be also interesting because, for example, I've told you that best matches in terms of LCA are not always the same as best matches in terms of closest similarity or highest similarity. And therefore, I think that the errors in estimated BMGs will be far from independent. So it will be interesting to have a look at this. And we're also investigating the relationship between best matches and orthology in the presence of HGT. We basically know that HGT, or horizontal gene transfer, is able to mess anything up, but if it occurs only moderately, then we think that we can probably extract a lot of orthology information from the graph still. And the last point that I've written down here is that we want to look at whether best matches can be used for gene tree reconstruction. So they are a bit of a different data that don't make this hard additivity assumption like for example neighbor joining makes. And you maybe remember that I've told you that every BMG can be explained by a unique least resolved tree. And this means in particular that the true gene tree must display this least resolved tree. So we're gonna have to look at whether this can be used to develop some method or integrated in some method to estimate gene trees. Yeah, and with this, I want to end my talk. This is all joint work with these people whom I want to thank. So Manuela Geis and Mark Helmut, who's also attending today, and Peter Stadler. And of course, I will also want to thank you for your attention. And now I think I'm happy to answer questions if there are any.